Now that we've recovered the orthogonality between our subcarriers using the frequency synchronization block, we're ready to take the opposite operation that we performed at the transmitter by taking the fast Fourier transform in order to recover the data subcarriers. And note that this block, along with all the other blocks in the receiver chain, assume that the cyclic prefix has been removed and any rate conversion techniques that need to be performed in order to get the relationship between the D to A rate and the fundamental have been performed. So let's go ahead and start by taking our time domain signal in. This is our complex baseband received OFDM symbol with everything done to it that I just mentioned. And now we're going to go ahead and, as we just talked about, and take the fast Fourier transform using LabVIEW's built-in function. And remember, we're going to go ahead and choose a false for the shift, as we've been maintaining that convention, and we want to stick with it for the remainder of the receiver chain. We're now ready to extract the positive frequencies, so we're going to go ahead and use the split array function. But now we need to figure out where exactly we want to break this array in order to properly retrieve only the data carriers and none of the zeros that we padded in between. To do this, we can take in the number of subcarriers, and then we need to do the same trick we've been doing all along, divide the number of subcarriers by 2 and compare it with a rounded and unrounded version of itself in order to determine if we have an even or odd number of subcarriers. So let's go ahead and do that now by rounding down and then taking the equality between the rounded and the unrounded version as we just talked about. Now once we extract the positive frequencies, we'd like to either keep the very first element in the case of the odd number of subcarriers, or discard it in the case of an even number of subcarriers where it's just going to be an injected pilot or absolutely nothing. And so in order to do that, we'll go ahead and use LabVIEW's built-in Boolean to 1, 0 integer function here, and we'll use that to eventually split our positive frequencies. So now we need to determine where we need to break in order to recover just the positive frequencies and the potential odd subcarrier or pilot carrier before bringing the subarray into the function here. And so in order to do that, we'd like to extract the very first component no matter what. So we're going to go ahead and add 1 to our rounded version. And we're going to break our array there. And now that we've done that, we need to figure out what to do with the negative frequencies. And so we're going to go ahead and take the second half of our first split array. And then, in order to recover the negative frequencies, we're going to take the total size and subtract what we just took from it and the number of subcarriers divided by 2. And with this, we now have the positive frequencies as well as the negative frequencies for our subcarriers, and we're ready to just build the array using the build array function built into LabVIEW and making sure that we right click and choose concatenate inputs. And now we have our parallel symbol out. If you have any questions, I encourage you to check out the See You Next module or email the author.